All right, let's start by looking once more at the Mathematica homework number 1 for tomorrow. I'm going to give you some guidance about one of the problems. In the section labeled Logistic Growth Model, there's a few different problems, and if you look down at exercise number 6, it's perhaps one of the harder problems, or confusing. What's the goal here? Your goal is to use manipulate and plot to make an animation of the right-hand side function, this thing, for this differential equation as c varies from -50 to 50. So initially what this means is you're not going to have to think about the differential equation, okay, initially. You're just focused on that function and you're trying to make a plot of it with the y-axis horizontal, and you can label the vertical axis anything that you want, z perhaps, or even f sub c of y. Make sure you type the product either with a space, c space y, or c star y. I always put a star, I try to always put a star as a default to make sure that that gets done as a multiplication and it's not treated as a single variable called psi, cy. Make sure you get good plot range to show the main features of the graph. Describe how those main features change as c increases. Oh, and yeah, here's the typo. That b should be a c right there. And then start thinking about how it's related to differential equations. All right, I'll talk about it a little bit right now, but the key thing as far as the book goes is in section 1.1, when they talk about the logistic model, there's a section titled Qualitative Analysis, about a page and a half long. It's the kind of ideas in there that you want to learn how to think about and explain with this example. You could focus on how many equilibrium solutions there are, where are solutions increasing and decreasing. And we're after approximate values here, by the way. Exact values are not necessary. So let's go ahead and do this to a certain degree here in class. Do I need to define a function here? Do I need to define f sub c of y? No, you don't have to. You could just type it in as is into the plot. However, to illustrate how to do that, how to actually type the function, and I'll go ahead and do it. I like going ahead and using a subscript for the c. It's bigger for you here. Going ahead and using a subscript for the c. And when you're first defining the function, again, use underscores, not just for the y, but also for the c. You actually don't have to put the c as a subscript, but I think that's a nice conceptual thing to emphasize that the c is not the variable you're plotting with respect to. It's the animation parameter for this family of functions. As c varies, you get different functions of y. Let's see, can you just copy and paste this? It might paste it as traditional form, and that might not work, but let's see what happens. Paste literal. Let's see what happens. Nope, that's not good. Okay, well, at least we can see it if I paste it down. Y to the fourth minus 4y cubed plus 9y squared plus c times y plus 20. There is your function.
Minus 4.
Thanks for catching that. We want to plot that and put that plot inside manipulate to make the animation. Now you don't use underscores. I said y, well, y can go wherever you want. You want to see the whole, all the features of the graph, the main features. It is a 4th degree polynomial with a positive leading coefficient, so the end behavior has got to be going upward as y goes to plus or minus infinity. But there might be some ups and downs in between. I'll just try -10 to 10 just to pick something initially. And see if we can see the main features of the graph. What kind of plot range should you pick? That's not clear as well. We can think about it a little bit though. The y-intercept is going to be positive 20. When c is positive, certainly the initial slope through the through the vertical axis is going to be positive. The graph will go up pretty fast probably. And when c is negative, it's going to be going down. It is y to the fourth. Well, let's just try. Probably need some pretty big numbers here. Let's try negative 500 to 500. Just to see what happens. I won't bother with coloring it. C is supposed to go from negative 50 to 50. Let's see what we get. All right, that is showing the main features. When C is negative 50, you see that end behavior going upward in both sides. And fourth degree polynomials can have at most 4 roots. This has 2 real roots I'm talking about. And can have at most 3 turning points. What are turning points? Local maxes and mins. This one's got 1. So you could describe that graph by saying it's got a local min at around 5 when C is negative 50. 2 positive roots at around 0.3 and 6.5. And is negative in between those roots and positive to the left and right of roots. Watch what happens now as C increases. Right about there, now we have 3 turning points, 2 local mins and 1 local max. Still only have 2 roots. Now we've got 4 roots, real roots. Okay, so as C increases, what you can say is something like this. Initially we have 2 positive roots when C is negative 50 or close to negative 50. As C increases toward 0, and we also have that local min, then we get a local min and a local max added. If C is around 10 or so, we got another couple roots that come into play. When C gets to about 32, 33 or so, now we have just 2 negative roots. Those are the kinds of words that you can use. Maybe about 4 or 5 sentences here. What about differential equations? I do say to relate this to differential equations. All right, the qualitative analysis. Well, this is the right-hand side function for a differential equation. It's an autonomous equation, just depending on y. The equilibrium solutions correspond to when this function is 0 on the right-hand side. What numbers for y give you 0 for this function value? That corresponds to constant functions equal to those roots for all t that solve the differential equation. Because the derivatives are always 0, and when you substitute in for y, that constant function, no matter what t is, that becomes 0 as well. So for example, when c is, you can draw some graphs. Well, I guess you can't really, you have to describe it in a minute here. When c is close to negative 50, there were 2 positive equilibrium solutions because there were 2 roots, 2 positive roots. You can say that in between, because f of y is negative, that means solutions are decreasing. Again, I'm drawing them for you, but you have to describe this in words. You could make plots too if you're ambitious. When y is bigger than 6.5, whatever that biggest root is, then f of y is positive, so solutions are increasing. And when f of y is positive to the left of the lower root, solutions are also increasing, so you get something like this. Okay, that's not a picture of a solution. It's the graph of this right-hand side function where y is horizontal. It helps you figure out what the solutions look like. And in section 1.3, it helps you figure out what the slope field looks like. That's a t-axis, and this is a y-axis in this picture. Y-axis is horizontal there, vertical here. It's okay. We can do that. Okay, these are the solutions. That just helps you figure out what they look like. That's the qualitative analysis. So it's a kind of confusing problem. It's fairly long, fair amount of writing to do, but I hope that gets you going. Any questions about that? Okay, let's talk more about slope fields, and let's talk about slope fields and ultimately something called Euler's method, not Euler, Euler. Don't say Euler. Okay. Euler's method. Slope fields and Euler's method. Let's talk about those in the context of the mixing problem. Although I do want to show you one more thing with this mixing problem with what we did before on Friday, before I get into slope fields and Euler's method. I want to show you how you can use DSolveValue in probably the slickest way that you can. So use DSolveValue right here to get this expression that defined my solution and stored it in this thing. And when we plotted that, I'll go ahead and enter this again. Excuse me. And when we plotted this, we didn't need to put the t in there. In a sense, it's like the t was already in there, because this symbol represented this expression that defined a function of t. Okay, it's a bit confusing, but let me use DSolveValue in a new way. I'm going to go ahead and enter this function down here, the right-hand side function as well. Copy and paste this down here. Actually, let's put it down here. I'm going to get rid of this q of t and just call it q. What kind of output does it return if you do that? Well, it is more confusing output, but in some ways it's better, as I'll show you. It's more confusing. It spits back the output as what's called a pure function, which is kind of a confusing idea. That word function is telling you this is a pure function. And what does this pure function mean? What does it do? Well, this is sort of a symbolic way of representing that solution that takes a number t and as input and sends it to this quantity as output. Let's take a simple example. If I type function t in curly braces, comma t squared, and actually the curly braces are not necessary here. What's going to happen when I enter this? Well, actually nothing. It just spits back what I typed. However, if I plug a number into this, like 4, it spits back the answer, 16. All right, if I plug another number in it, like, well, let's use a symbol like z, it spits back z squared. Now, you might think that's kind of strange. Why not just do functions in the way we're always doing them? Why do it in terms of this pure function? One reason is that sometimes when you're coding, it's nice to not have to bother giving functions names, but you'd like to be able to use them. That's one reason. And so in a sense, we are using the squaring function without giving it a name like f or g or h. Okay? And there's a shorthand syntax for this that can save some typing as well, though I'm not going to get into that here. Another reason is, well, I guess just for this, what I'm going to use it here for differential equations. It's going to allow me to store this pure function output that I get from DSolveValue when I just have the dependent variable there, not the independent variable, in another quantity and graph it. I'm actually going to call the quantity phi, escape ph, escape, because it's going to represent my function. Now this pure function, this function that takes the number t as input and sends it to this quantity as output, is now stored in the symbol phi, and now I can evaluate phi, for example, at t and get that output. And now I can plot phi as a function of t. It might seem like it's more work than it's worth, but I claim definitely in the long run it's going to be better. Okay? And we'll hopefully see that. That's our first little mini lesson in pure functions. It's probably not something you can get in 5 minutes. You have to work with it again and again and again. Okay? But I will save this on Moodle and you'll see the syntax. Also in those extra videos that I made,
There are about 10 videos about using Mathematica for differential equation. Along about video number 6 or so, I think I talk about pure functions more.
All right, so that's what I wanted to show you, something sort of the slickest way to use DSolveValue. We'll see more examples later. Let's go down now to the slope field section here. And let's go ahead and use this FTQ, f of t comma q, my right-hand side function for the differential equation. And as we did last Friday, let's graph the slope field. But before I graph the slope field with VectorPlot, let's make sure we understand what it means. When you plug in a point, a t-coordinate and a q-coordinate in this case, usually it'll be a t and a y-coordinate, like the point t equals 1, q equals 3, you're going to get a number for output. This is a function of two variables. As is, you would think of t and q as both being independent variables for this function. However, when we relate it to the differential equation, having a dq dt on the left-hand side for that differential equation, then q becomes the dependent variable and t is the only independent variable. But as far as the slope field goes, you get this number, 7.75. And in the slope field that you make, axes labeled with the variables, t and q in this case, though again, usually it'll be t and y. At the point 1, 3, you make a little line segment with a slope equal to 7.75. Now, of course, when you're drawing it by hand, you can't get it perfect. 7.75 is going to look pretty steep there. Rise over run is going to be 7.5. If I follow this line forward, 1 unit of time, the change in y would be 7.75. It would be up at 10.75. All right, and I can do that theoretically at any point in the plane that I want. This is a perfectly nice function. Well, I guess I can't do it when I'm dividing by 0. Sorry, it's not perfectly nice. This is undefined when t is -1. So along the vertical line at t equals -1, you would not draw any slope marks. Or if you did, you might think, well, maybe I should draw them vertical. And sometimes that's okay, and sometimes it's not. Okay. We're staying to the right of t equals -1, so I'm not worried about that. Again, I can do this at a bunch of different points. I'm not going to, because now I want to use the computer. All right. This is non-autonomous. It's also not a pure antiderivative problem. There's no real quick way to sketch the slope field based on thinking about it being constant along horizontal lines or vertical lines. It's not. That would take a lot of work to try to figure out what the slope field for that looked like by hand. We definitely want technology here. And that's where VectorPlot gets used. Again, how do you do it for slope fields? Use curvy braces here. And for slope fields, the first input is always 1. In chapter 2, we'll talk about vector fields. And for vector fields, you use VectorPlot, and the first input is not always 1. The second entry for this list here is the right-hand side function, f of t comma q. Let t go from 0 to 10. Let q go from 0 to 50. There's the basic plot, though it doesn't look so nice. Let me do the extra things to make it look nicer. So like get rid of the frame arrow false. Actually, you don't have to get rid of the frame, that's my preference. Include axes are true. I think you should include axes whether you get rid of the frame or not. Axes label, TQ. Actually, let me go ahead and show you what I hinted at last Friday, that you can use what I call text and style built-in functions to make bigger and italics versions of T and Q. If you do this, text style, T in quotes, and then put comma, large, italic. That'll make T large and italic. Do the same kind of thing for Q in this case. So again, usually it'll be a Y. There we go. Now T and Q are large and italic. So it looks nice. We don't want these funny looking arrows in here, so that's where the vector style comes into play, and you can pretty much put it anywhere in here if you want, after any comma. Vector style, again, it's 0.03, 0.03, none, is what I copied other people doing to get a nice picture. Oops. That's not good. Oh, it's vector scale. Vector scale. I always get those confused. There we go. Vector points, can make more of them. Again, I think the default here is 15 in each direction. So if we do 20, that'll be more in each direction.
What happens if you use different numbers for the vector scale?
I can make them shorter. I think, like if I put 0.01 here, I can make them shorter. That might look better here. Yeah, that looks better maybe for this one at least. I think vector style can be used to color it. Vector style, for example, green. A little hard to see there. Okay. So you can make the slope field based on the right-hand side function without ever thinking about differential equations at all. You can make pictures like this. Now we want to relate it to differential equations. In this case, dq dt equals f of t comma q. That's the formula there. It's a non-autonomous equation because there is a t explicitly on the right-hand side. It's also not a pure antiderivative because there's a q. It's a mixture of t and q. The slope field is not constant along horizontal lines or vertical lines. It's more complicated. You can see it by looking at that. Solutions have to follow the slope field. In effect, what this differential equation is, here's me pretending. What the differential equation is communicating with the solution is, follow the slope field. Make sure you follow those little line segments in such a way that your derivative, dq dt, your slope at any point t comma q, is given by the output of this function at that point. So that any time a solution passes through, ideally the midpoint of one of these line segments, I guess I'm not absolutely sure that if I made some solution curves in here that it's going to go through the midpoint. But ideally, anytime your solution curve touches the midpoint of the line segment at that point, that line segment's got to be a tangent line for the solution curve. The slope of the solution has to match the output of the function at that point. Actually, let's go ahead and use DSolveValue in kind of a fancy way here, in a nice way. I'm going to go ahead and use the phi. But I'm going to put a subscript on it. I'm going to call the subscript Q0 for the initial value of Q. I think I can get away with a colon equals pretty much any time. But let's use DSolveValue. I've already defined my function f, so I can type the right-hand side in there like that. And again, you need the t there for Mathematica. Not by hand, but for Mathematica. I'm going to put an arbitrary initial condition here. And to make use of this,
As a pure function, I'm just going to call this q instead of q of t, and put a comma then t. This pure function thing now is stored in this symbol, and now that's going to allow me, because I've allowed my initial condition to vary, I'm going to be able to make it manipulate, where I change q0 and I see different solutions. So put this in manipulate. I'm going to need to show a couple different kinds of graphics. I'll close off the vector plot one here. I think I'm going to put the frame and the axes outside of the vector plot. Oops. Okay, I ruined my copy and paste here. Frame, arrow false, true. Still inside the show, this is the last bracket for the show. No, that's the last bracket for text here, excuse me. This is the last bracket for show right there. So this stuff is still inside the show. I haven't finished off my manipulate yet. Q0 is going to be the animation parameter. Started at 0 and go up to say 10. What else am I putting in here with the show and the vector plot? I want to put a regular plot of my solution. Phi sub Q0. Phi sub Q0. Now don't put an underscore. You do need to put a T here, actually. Whereas with the sol, the first few minutes of class, we didn't need to put the T. If you use and DSolveValue in the way that I'm doing, you do need to put the T there. It's kind of like because I had to evaluate the pure function at z, I had to put the extra z on the right. That's the reason why. Again, the model is only valid for 4 minutes. There we go. Now let Q0 change and you get a different initial condition. And different behavior to the solution. Both of these are, all these are increasing, but when Q0 is small, the graph is concave down, and when Q0 is large, the graph is concave up. That's a different kind of behavior. It does seem possible that maybe there's a constant, not a constant function, but a straight line that solves the differential equation. Maybe with a y-intercept of 3 or 4, and a slope. Actually, I know the answer is 4. Y-intercept of 4, if Q0 is 4 to start off with, this actually is a straight line, and I actually know the slope of the straight line is 4 as well. I claim Q equals 4 plus 4t solves the differential equation. It's the only straight line solution. It's not an equilibrium solution because it's not constant, it's not horizontal, it's slanted. But it is a solution whose graph is a straight line. It is a linear solution. Let's check it. The left-hand side, the q to t is always 4 for all t. The right-hand side better be the same thing for all t. 10 minus 3 q that whole thing cancels with this whole thing to leave a 2, right? 2 times 3 is 6, and minus 6 is 4. That's true for all t as well, as long as you're not dividing by 0, which we're not when we're considering initial value problems where t is greater than or equal to 0. So for all allowed values in the domain of your solution, the left-hand side and the right-hand side do simplify to the same thing. That linear function is the solution of the differential equation. Could we have seen it in the output of DSolveValue? If you replace Q0 with 4 here, evidently this simplifies a lot. Those 4's cancel. It's not obvious. I guess you'd probably want to factor out a square root of 1 plus t and do some cancellation with the 3/2 power in the bottom to just leave 1 plus t in the bottom. And then evidently maybe you can do more simplification. Give it a try. I won't take the time right now, but that's something you can check. Okay? And you should think about what this means, by the way, for the real life model. Okay? We had initial condition of 0. One thing it's telling you is when the vat is full at time 4, you're close to 20 grams of salt. A little less. What's the value of the solution with the initial condition q is 0 equals 0 at time 4? There's the exact form. That's approximately 19.64 grams. You can also figure out the concentration. Not just the amount of salt. If I divide the amount of salt by the volume of salt water in the vat, 2 plus 2t, that's a function that represents the concentration in grams per liter. And that's heading toward a horizontal asymptote if you let t go to infinity, at least at 2 grams per liter. Which makes sense because, guess what? The concentration of the salt water going into the top is 2 grams per liter. So your concentration of the salt water in the vat is approaching. In the long run, if you could keep filling the vat and keep mixing it up, it's approaching the concentration of salt in the inflow. Any questions? Please stop me if there are any questions. I have a question. Any questions? Get it? All right, so the computer's nice to make this stuff. The slope field and the solution curve with DSolveValue, excuse me. But what if we don't have a computer? Is there any hope of either finding the solution or finding some values of the solution without a computer? Well, in this example, there is hope. You actually can solve the equation analytically. In section 1.8, we'll do so. Actually, the title of section 1.8 is the linear equations. And this thing is solvable with some basic techniques. We can find what DSolveValue found. Though you saw the formula was kind of complicated. However, if I, for example, put a square on that Q, which would not be a good idea if I wanted to be an accurate model, but if I didn't care about real life and just felt like playing with the math and put a square up there, probably all bets are off as far as finding a formula for the solution. You probably wouldn't be able to do it, and probably Mathematica wouldn't be able to do it either. I suppose I should try, just for fun. Can't Mathematica do it? Just for fun, let's put a q squared up there. Still no problem with the slope field. The slope field still exists. But do you have any chance of finding a solution with DSolveValue? I doubt it, but I could be wrong. Well, kind of. It involves functions you've never heard of. Bessel I, Bessel K. Evidently, those are Bessel functions, whatever that means. Okay? There are plenty of functions you've never heard of. They're called non-elementary functions, Bessel functions being one example. Other examples I can think of off the top of my head include Jacobi functions, the gamma function, the error function, ERF. Actually, I do talk about that in Calc 2, so if you have Calc 2 for me, I talked about those. Okay, these are non-elementary functions. You can't represent them as ordinary kinds of formulas. You can calculate with them. You can still approximate their values because you can still define them. involving things that allow you to do approximations. But yeah, that's pretty nasty. What would happen if I made this a cube? Will it give up? Uncle. I think it's going to give up. Yeah, I gave up. Didn't know what to do. There's no special name even for the solution. Okay? But again, the slope field can still be made. And because the slope field can still be made, and because this is a perfectly nice function, at least when t is greater than -1, you would think there should still be a solution. Or solutions to initial value problems. Is that true? Yes, the answer is, it is true. You can prove abstractly that this has solutions to initial value problems, starting at t equals 0, any initial value problem, starting at t equals 0. But there's just no formula for the solutions, which is kind of a strange thing. How can you prove they exist if there's no formula? That's the subject of section 1.5. We won't actually do the proofs in full generality, but it's called the existence and uniqueness theorem. I'll talk about proofs of simpler cases. You can prove solutions exist even if you can't find a formula for them. And therefore, we can still try to approximate them. Let me go ahead and do that. I'll stick with this cube example that doesn't have a formula for the solution. Again, no application here to the mixing, okay? Forget about the mixing problem now. This is just a pure math problem. Oh, let's switch it to a y to be consistent with what we usually do. Okay? So if you're confused, if you think you might think this is a mixing problem, write a note to yourself if you're taking notes. Not a mixing problem. Let's add an initial condition in here, make it an IDP, y of 0 equals 0. Let's keep that simple. How could we possibly approximate the solution if we don't have a formula for the solution? And evidently, if there's no hope for finding a formula.
Wait, we want it to be divided.
Yeah, thanks. Well, think about what tangent lines do. Tangent lines to smooth curves approximate the smooth curve near the point. So if I could find the slope of the tangent line to the solution at this point, I guess I could follow that tangent line forward a little bit. And I would get a good approximation to the solution initially, at least. Does that make sense? What's the slope of the tangent line at that point for the solution? It's the value of the function f, the right-hand side function at that point, 0, 0. F of 0, 0 equals what? Plug in t equals 0, y equals 0, get 10. The little slope mark has a slope of 10. Now, should I follow that 1 unit of time into the future? No, I think it's probably not a good idea. I think we want a smaller interval of time. Maybe 0.1? Let's go ahead and pick 0.1. That's t equals 0.1 there. What's the y coordinate of that point right there?
0.
This one?
1.
1. Yeah, slope of 10. T increased by 0.1. The change in y will be 10 times 0.1. 1. So that straight line is hopefully a pretty good approximation to the true solution curve between t equals 0 and t equals 0.1. What should we do next? Well, now use the value of the right-hand side function at this new point to find the new slope of the corresponding slope mark in the slope field. And follow that one. What's that point? That point is t equals 0.1, y equals 1. plug it into f. Plug it into the right-hand side function for the differential equation. 10 minus 3 times 1 cubed over 2 plus 2 times 1. 10 minus, stop me if I make a mistake. Oh yeah, I made a mistake. T is 0.1. 0.1. 10 minus 3 over 2 plus 0.2 is 2.2. Right? Three divided by 2.2, about 1.36. In the end, this simplifies to about 8.64. So the slope mark at this point is not as steep. Not claiming to draw this perfectly by any means. Now go to t equals 0.2. Find that coordinate, whose first coordinate is 0.2. Second coordinate. It's going to be what? It's going to be up to 2. Delta t is 0.1. Slope is about 8.64. Delta y will be approximately 0.864. This is going to be 1.864. Etc. I don't feel like doing any more by hand. Let's have Mathematica do it. Okay, I sort of lied a bit and said, well, what if you had to do this by hand? I mean, yes, you could do it by hand, but it would be a big pain. Let's have Mathematica do this. We're implementing something called Euler's Method. As a system of recursive equations, it looks like this. The next value of time, the k plus first value of time, if you will, is determined by the preceding value of time, the kth value, plus the change in time that you're allowing. In this case, it's 0.1. It's the preceding value plus the change in time. This is called a recursive equation. Okay? T sub 0 is going to be, in our example, it's going to be 0, the initial condition. We're going to start at k equals 0. T sub 1 then will be delta t. T sub 2 will be 2 delta t, etc. in this example. Technically speaking, t0 could be something other than 0. It could be 1. If that were the case, then this would be 1 plus delta t, and this would be 1 plus 2 delta t. But usually t0 is 0, and so usually t1 is delta t, and t2 is 2 delta t, etc. That's how you update the first coordinate along your approximate solution curve. I say the word curve loosely here. It's really a polygonal curve. It's a bunch of line segments connected together. How about the second coordinate? How about the y coordinate? Think carefully. This is the hardest part. How do you find the new y coordinate in this one here? y2 is about 1.864. How do we get that from the old y coordinate? Well, you take the old y coordinate, y sub k, and add the change in y, delta y. But what's the change in y? How do you find the change in y? I use the slope field, right? How should I write that in general? I took the slope and I multiplied times delta t, right? 10 times 0.1? to get a change in y equal to 1. And then 10 times 8.64, excuse me, 8.64 times 0.1 to get 0.864. How could I write that symbolically? Using only that symbol and the delta t.
Why'd we get 1.861?
Because we added 0.864 to the previous y value of 1. Tell me, what should I write here?
Just f of ty.
Yeah.
times delta t.
And delta t. But if I'm going to do it in this recursive scheme, I should not just put a t and a y here. I should put the preceding values of t and y, which are t sub k and y sub k. Okay, for the sake of time, I'm going to implement this in Mathematica in the fastest way, though this way is going to be confusing. But I think we better do it this way because the less confusing way bogs down. It's not as computationally efficient. So what I'm about to do is going to be confusing, but you can just essentially copy and paste what I do. Okay? Let's go ahead and define what delta t is. Actually, let's not. I'm going to do what I do in my solution key. I'm going to define a function that I call g. It's going to have a subscript of delta t. It's going to be a function of t and y, just like little f is. And what is this function going to be? And actually, I forgot I put curly braces around t and y. Well, essentially, what we're going to do is g is going to represent the iteration of this system of recursive equations. G is actually going to be a function that takes two inputs, t and y, and gives you two outputs given by these two expressions. Though I'm not going to use the subscripts here. I'm just going to use t and y. This is the confusing part. Well, one of the confusing parts. I'm going to go t plus delta t here, and y plus, not delta y, but f of t comma y, I don't think I need curly braces here, times delta t. This is confusing. Again, in a nutshell, I'm taking this system of recursive equations and I am sort of letting g represent that system except without the subscripts. And then what I use is a command called NestList in Mathematica, which does iteration very efficiently. We're going to iterate this function. We're going to use it over and over and over again. That's what it means. Effectively using these equations over and over and over again. I've got to put the g as the first argument. I want to put my initial point as the second argument from the initial condition. T equals 0 and y equals 0. T will almost always be 0, but y will not necessarily be 0. It is for this example. So I put a 0, 0 inside curly braces next. And then the final thing is the number of iterates. And I forgot something here. I forgot a subscript for this g. I need to specify what delta t is going to be. Delta t is going to be 0.1. Let's do 10 iterations of this. It gives me a list of points, a list of lists in Mathematica, but I'm thinking of it as a list of points. The first of which is 0, 0, the origin, where I started. The second of which, look, is 0.11. That point right there. The third of which is 0.2, 1.864, yay! Right there. If we had kept going by hand, we would have gotten the next point to be 0.3, 2.055 approximately. Okay? That's the quickest way to implement Euler's method. Give me 30 seconds here. I'm going to store this in a list this list in a variable I'm going to call EM. EM stands for Euler's method. And then I can also plot it with list plot. List plot plots points like this. And something surprising happened. There's like a little dip here. Interesting. I don't know if that's numerical error or if it's an accurate reflection of what happens. I'm not sure. It could be numerical error. Numerical methods do produce error. You're not going to be exactly right. Okay? That's the quick way to implement it. You'll see it in the solution key for the completion problems.